Hello there. Welcome to the AMA session for our deep learning courses. Um, can you hear me fine, Daniel?
Yeah, I can hear you well.
Okay, great. Yeah, welcome. So as you see here, I'm currently showing one slide that pretty much sets the context. Oh, slight audio problem. I had a massive amount of feedback just now. Um, Okay, so where was I? Yes. So the slide here basically sets the context. If you're not familiar, we have partnered with Deep Learning AI to provide a set of short courses on federated learning. And so if you want to take the course, if you've stumbled across this AMA and we're not aware of these courses, well, you can follow this URL on the slide here. You can take one of these two courses. We'd recommend you start with the first course, which is about Introduction to Federated Learning, the basics. And then we've found most often people are quite curious these days about LLMs, large language models. And then we wanted to describe how these align and fit with the properties of federated learning, and in particular, the benefits they can afford things like private data. So this is a great pairing, I think, for people to do to kick off their learning about federated learning. Um, before we before I introduce everyone who's here and we get underway, I also want to describe how this AMA will work. We're essentially live casting right now the questions that we're going to be seeing in the Slack channel on the Flower Slack. And so if you're interested in these courses, or if you have questions about federated learning more broadly, then we'd ask you to join the Flower Slack now, where you can post your questions. You just move to this course hyphen deep learning hyphen AI channel, and you can start to pose your questions, and we'll answer them right now for you. The link to join the Flower Slack is this QR code that you see. And that's everything you need to know. So I think how about we just do a round of introductions? Um, so my name is Nicholas Lane. Um, I helped make one of these courses. It was a real pleasure. And I'm happy to be here to answer any questions you might have. Over to Daniel.
Hi, my name is Daniel. I'm one of the instructors on one of these courses. On the first course, Introduction to Federated Learning. In this course, in the Intro to Federated Learning, we really start from zero and then take you in small steps all the way to building and tuning and benchmarking your first federated learning projects. And I'm excited about the AMA today. Generally, I'm also one of the creators of the Flower framework. And with Flower, we are aiming to build one end-to-end solution that allows you to just toy with projects, build small demo projects, and then step by step make those projects more sophisticated and then take them all the way to a production deployment. So you can start out with simulation, build your project, experiment with new ideas. Many researchers use Flower to build projects to submit papers to leading conferences. But then you could take these projects all the way and also deploy them on real-world distributed data. Over to Javier.
Hello, my name is Javier. I'm a research scientist at Flower, and I've been helping putting together some of the materials for this course, which, as you probably have seen or you will see if you take part on the course, it runs with Flower simulations, which is my main focus these days on Flower. Yeah, looking forward to hear your questions, and if you have any other questions after this AMA, then we'll be also very happy to answer them on Slack. Over to Mohammed.
Hello everyone, my name is Mohammed. I'm a research scientist at Flower Labs, and I mainly help with preparing the privacy aspects of Flower in both courses. And today I'm happy to take any questions about privacy and specifically differential privacy in Flower.
Great. Well, since launching the courses, we had a lot of people take them and start to pose questions to us. And so we've collected up a number of questions here that have been asked previously, as well as some of the questions that are sort of coming in. So I think we'll just start to work our way through them. Feel free to join the Slack channel to ask your questions live, or we'll just start to take some of these async ones as well. So the first question we've got to run through is we've seen variations on this question a number of times. And basically the question is, they say, I've used the notebook, but how can I run this on my own machine? And they say something like, I want to run this on a GPU, I want to run this on a beefier machine, and so on. So I've seen this number of times. I think, Daniel, do you want to take this one?
Yeah, absolutely. So maybe to set a little bit of context first, you can use Flower either in a notebook, as you've seen in the DeepLearning.AI environment. You can take those notebooks. You can also put those notebooks run them on Google Colab, for example. But then obviously you can also run all of this code on your local machine, and you can either run it using the notebooks, using the run simulation function that you might have seen in the course, or you could also just build plain Python code without using notebook environments. And you can do this for both simulation. So in the notebooks, we use the simulation engine that Javier also mentioned. The simulation engine is always a great choice if you want to execute something, maybe just on a single machine, or if you don't have a ton of resources, because the simulation engine helps you to make the best use of the resources that you have available on a single machine. And you can use that to simulate pretty large numbers of clients actually on a single small machine. But then in addition to that, Flower also comes with what we call the deployment engine. And the deployment engine allows you to put this code onto different machines. Obviously, federated learning is a distributed approach, sometimes also called decentralized approach, where you have data in different hospitals, for example, and different organizations, or you have data on different user devices. So obviously you need to be able to also run this in a distributed fashion. And we call this mode the deployment engine, because this is most usually used in proper production deployment on real world data and real world organizations or on user devices. For running this on a single machine, maybe I could actually give a quick demo for how this could look like in the latest Flower release. So let me share my screen for a second. Or I'm unable to share my screen. Is there some setting we can change?
No problem. 1 second. Bear with me 1 second. We can do this.
I can already prep everything here. It's no problem.
We should be good to go.
Okay, great. So you should now be able to see my terminal window here. What I have here is just a plain terminal on a plain MacBook Pro. And what I'm about to show is, I think this is an environment where I've already installed Flower. But just to repeat the step, you would do a pip install flwr, and then because you want to use the simulation engine, you would do pip install flwr simulation. That will just install a plain Flower library with all the dependencies necessary to run a simulation. The next step, and this is the first thing that's pretty easy to remember, is the flwr command. So you can do flwr new to create a new project. Let's do flwr new, and then the prompt asks you to input, for example, the project name. Let's call this, I don't know, AMA demo. And it asks you about your Flower username. So this is the username you can register on flower.ai. You can also put anything here. This is Daniel in my case. And then the next step, it asks you about the ML framework that you would like to use. So the Flower New command comes with templates for different frameworks. In the DeepLearning.AI course, we use PyTorch, but you can use Flower with other frameworks like TensorFlow or MLX, JAX, or also plain NumPy. In this case, I'm going to choose the MLX demo because I'm on a Mac here. And then last but not least, it tells you what to do next. So it tells you to CD into the new project you created, and then to pip install the dependencies, and then to Flower run it. Let's do that. So we're going into CDing into the AMA demo, and then we're going to do pip install -e dot, which is the current project. And this installs all the dependencies you need. For example, we chose the MLX template, so this is going to install MLX. Now, before we run this, let's just take a super brief look at the code. I want to leave enough time for other questions as well. But what you can see here is that you get a pretty simple project structure. You get a README that explains how to run this properly. You get a PyProject.toml that lists the dependencies. So you can see MLX here because we have the MLX template. You can see Flower simulation, you can see Flower datasets and NumPy. And then a number of other things that I won't go into just now. And then in the AMA demo package, you can see plain init.py. You can see the server app, the client app that you're probably familiar with from the course. You can see a server app, and you can see task-specific things like the MLX model we're about to use here. And then with that in place, you're already able to run the project. And the easiest way to do this is to just call flwr run dot, because you're running the current project that you're in. So let's run this. You can see that it's loading up. It's initializing parameters of the model. And then we should see the training start pretty quickly. We can see round 1 is starting. We can see that 10 clients were sampled out of all 10 clients that are available, which is the simulation setting that we use, 10 clients. And then we can already see round 2 and 3, and we can see the loss going down, which means the model learned something. I think that that should be sufficient. So the two things to remember are FLWR new and FLWR run.
That was awesome. I think that might be one of the very first times we've demoed this feature so widely.
It's true. We just released it last week on Wednesday in Flower 1.10.
Awesome. Let's go to another question. So this question we got a few days ago, it is basically saying they saw Flower simulation was happening in these courses, in both of them, I believe. And then the question was, is this doing real FL? Is this really doing FL? Or what does it mean by simulation? What parts are simulated? What parts are not real? And so on. It's a natural question, I think. Wasn't really enough time to sort of mention that in the course. But luckily, we have our resident simulation expert here to answer this question. So over to Javier.
Yes, well, it's a good question, actually. It seems like a very superficial question at the beginning, but there's a lot of depth here. I think it depends on how far you want to take the simulation. Like usually when people do simulations, at least what I've been doing in the past is you have a new algorithm, like let's say a new aggregation function in FL where you want to have a new way of combining different models from your clients. And then you just want to focus on how good that, let's say, function is. So in order to do that, what you want to do is simulate different conditions, like you want to have more or less clients, or you want to partition a data set in a way that the setup is very simple or very complex. So this flexibility if you go to the real world, the data is what it is, and you cannot change it so easily or at all. But in simulations, you have all these degrees of freedom. So I think that's the main purpose of simulations. When it comes to the specific part of the question of how realistic this is, I think it depends. It's never going to be as realistic, but you can introduce many mechanisms to make it more realistic. You can simulate, for example, clients dropping. This is something that happens in the real world. You can simulate dataset partitions that more closely follow what a real population might have on devices or in silos. Things like that. You can simulate some clients having access to more compute resources than others. That happens in the real world. If you think, for example, of smartphones, some smartphones are more powerful than others. So I think simulations in general, probably you don't want them to be completely super close to the real world, because it would be a very challenging scenario for things that might not be so needed to test your particular, for example, algorithm you are developing. But for everything else, I think simulations brings flexibility, basically. Maybe you want to add something to that, Nick. You are also doing a lot of research.
Oh, well, I think it's a fascinating area. And the first thing that jumps to my mind on this topic is that essentially, I think an important factor with Flower is that you can actually take the same code that you run in simulation, then run it in deployment. And it's not a capability that I see in many other frameworks out there. And I think it's really useful to have this. So it means that you can experiment with things, and then it's a very few number of changes to actually launch. So that's one main factor. And then I think there's a lot of work to be done still in simulations, because it's a natural area of the workflow of people trying to build federated systems. And so we need to have various kinds of simulations, I think, to allow them to kind of experiment before they launch, as to how well this thing is going to behave. You've got the sort of machine learning part of it, just like, is it going to converge? But then you've got other parts of the system that you need to kind of like dial in the realism in between, and then it has to be very fast. And so I think we have a great solution, but I still think we can add even more to that solution to kind of help people go from, zero to hero in that sort of space.
Yeah, I agree. I think one part that we have made a lot of progress is in making it very easy to simulate different type of data partitions, which is with something we have called Flower datasets. We can maybe talk about that later in one of the questions. But yeah, I agree that there are many other components like connectivity between clients. We can simulate different scenarios and things like that. So it's a very big topic.
Cool. Well, let's start diving into these other questions we've got. So we've got this question, what is a good data set for testing a federated algorithm? And anyone here want to take that one?
I think, well, just following same ideas I mentioned earlier, you want to have a wide set of data sets that you use to evaluate your algorithm. It's fine to start with simple setups like, I take, I don't know, Cypher10, or I take Feminist, things like that. But then if you want to really deploy it in the real world, you might want to have more challenging data sets, maybe Ready dataset, or others that are for sure naturally partitioned data sets. Those are which datasets in particular. I think the ones I've mentioned are a few of them. There are also datasets. Not everything is about images, right? There are text datasets like the ones in the course for the deep learning in the second course of the project for the medical Q&A questions. But there are many more. Is there one dataset specifically used in the privacy settings or things like that, Mohammed?
No, in course one, we use image datasets, specifically MNIST.
I guess it's also worth mentioning that there is the Flower datasets library, which can help people enormously in this respect. I think something that's a problem with federated learning, at least in research papers, is inconsistency as to which data sets people use for benchmarking, and then also how they're treating those data sets. How do they work with them? And so that is our answer to how you can start to normalize that effort and hopefully get people focused on the sort of other parts of the experimental apparatus. Yeah, so I've got a bag full of these questions from folks. Like, we can just dive in here. I've been asked to remind people also that because we had quite a few people wanting to just directly ask questions on YouTube, we didn't realize this was a facility, so we've now enabled the chat on YouTube as well, in case people want to ask questions there. Feel free to do so. Anyway, let's look at this question here. The question is, can you explain DP to me? And I think, Mohammed, you're the right man for the job here. So can you give someone that have taken the course is flying by, a lot of stuff's happening. What would you say to somebody after taking the course and they ask that question?
Sure. So by definition, differential privacy is a mathematical framework, and the privacy standard designed to provide privacy guarantees about the privacy of individuals. Just to give you an example, let's say we are 4 people in this virtual room, and someone asks about the sum of the age of all these 4 people, and we give a number. And then one of us leaves this room, and that person is again provides that query, and we give another output. And by just deducting those outputs, that person can basically infer the age of the person who left the room. And differential privacy actually provide the privacy for that individual by adding some amount of noise to the query outputs that we give to that person. And that amount of noise is kind of calibrated and depends on factors like how much privacy we want to provide. And there's also a trade-off between the amount of privacy that we want to provide and the utility. So the more privacy actually results in less utility. So this is the concept of differential privacy. And then in federated learning, depending on like what entity we want to provide privacy, we have different variants of differential privacy. For example, we have central differential privacy, which the idea is that we want to provide privacy for the clients, for the whole client's data set. And this is achieved or let's say performed by the server. And we also have local differential privacy that each client actually provides privacy for its data points. Basically, they don't trust the server to perform the privacy. Yeah, I think that's about differential privacy.
Okay, it's a good summary. Well, I'll just keep on diving through these questions. Another question: is this the same thing as is done with the Google keyboard? So they've heard about this Google keyboard application of FL. I think it's referred to in the course. Of course, Google was one of the sort of key pioneers, especially of taking it to production, but doing many things. And so they're just basically asking the simple question: is it the same thing as they've heard of with the Google keyboard? Daniel, what would you say to this?
Absolutely. So I think that the short answer is yes, it is, but then we should put a little asterisk on it and just clarify a few of the details. So first of all, yes, it is. The Google keyboard is probably one of the most impressive examples of federated learning that's deployed in production, just because of one of the reasons is the large scale that it is deployed at. The Google keyboard runs on hundreds of millions of Android devices, and this is, I would say, a fairly substantial federated learning deployment. In that sense, it's also driven quite a bit of federated learning research, and there's and the team behind it, and there's several teams working on that. have done some amazing work in the space, also related to differential privacy and other things. So what I want to add as a little asterisk is that sometimes in cases like the Google keyboard, it's not just vanilla federated learning that is being used to train those models, but it's sometimes a combination. So what is a very reasonable approach is, for example, to take the model and then pre-train the model on some data that you already have in some public data, perhaps pre-train it in a centralized way, and then continue to fine-tune the model in a purely federated fashion. And there's very different ways in which you can combine centralized training, but then also federated fine-tuning or federated training. And you can, similar to the training aspect of it, you can also use the evaluation aspect in a similar way. Maybe you have some high-quality evaluation data. You train the model in a federated way on distributed data, and then you evaluate it on your holdout evaluation data on the server side. Or maybe it's the reverse. Maybe you have some data that is distributed across different organizations, and you want to use this data to get better evaluations of the models you train, but you train the models in a different way. So there's a lot of, the point I want to get across is that in production settings and in many projects, there's different combinations of centralized and federated that you can do on either the training side or the evaluation side. And then, what I should also mention is that related to this, there's also federated analytics, where it's, strictly speaking, it's not about training or evaluation of models, but it's more like a SQL query that runs across distributed data. This is also a technique that is often brought into the mix to, for example, better understand the distributed data that is available without having to collect this data first. So the gist is, in a production setting or in any real-world project, there's often a combination of different techniques that are applied in a way that makes sense for this particular project.
Cool, makes sense. That's a very good. I like how you broke it down into the short answer and the long answer to give the full context. Next question is something we hear from people, particularly where they're just getting to understand federated learning. And so where they have perhaps taken a machine learning course, they've learned how training works and happens. Maybe they're still fairly new to how that works. And suddenly people start telling them they can use federated learning as well. And initially they're sort of wondering, how can this training be possible if you're only sharing model weights? Because they've learned about how training happens. There's certainly a different type of data being shared. And so how on earth is this even possible? Who would like to take this question? The question would be, how can this work at all if you're just sharing weights? Maybe Javier. I got a feeling you want to take this one.
I can try. So while you were repeating the question, I was thinking on the original setup where we have only centralized training, and then we train with different batches, right? And after every batch, our model gets updated with the gradients. So you can imagine that now we have 4 different training setups of the same model, and they all update one batch, the model. Then in some way, I think we need to take some steps, but after these models have been updated once, you could fuse them together and they won't be so far away from the original point before starting any kind of training. I don't think I'm explaining that very well, but I think one way is that I think one good example is gradient accumulation, but might be a bit more advance of a concept, so you delay the application of gradients a number of patches, you can maybe think about it, how aggregation works in federated learning. But I think the short answer is that and then you have different models that have been updated locally in slightly different directions because they all have the nodes that have different data. And as long as this data is kind of like from the same underlying distribution, like all they are images of certain categories of objects, for example, you can take the average of the resulting models and things work. Convergence might be slower. It might be even slower if distribution of the data is very different in different nodes. This is one of the open problems in federated learning, but in practical terms, it just works. Maybe it's not a very convincing answer for the most skeptical in the audience, but
yeah, as I was asking this question, I realized that it's kind of difficult to just give a verbal answer that sounds quite convincing, actually. So I was thinking, what would I mean, another way that I'd explain it, I think, is if you've taken a course and you've learned how training works and you're comfortable with that, then all federated learning is doing is repeating those centralized trainings in isolation from each other for each client. And so each client, therefore, if you believe if you've understood how centralized training and conventional machine learning works, then each of these clients is just performing that by itself and in training an independent model. And then all that the averaging step is doing is really looking for a set of weights that is sort of in a set of weights that on average would be in the midpoint of all those models that are found. Now, that's sort of not a very technical answer, but it's essentially what you can kind of think of in terms of intuition. And then I guess one detail and difference between what I just described and what actually happens during federated learning is that we don't let these models train all the way to completion into the averaging. We just do this averaging a number of times along the pathway to finding those ideal set of weights. And that's because if you let the individual models train, because they all have a very localized, isolated view of the data that's separate from each other, if you let them just keep on training without ever doing this averaging step, that is some sense doing a synchronization between them, they could just drift off to being very different parts of kind of the weight landscape, or when they're trying to find this ideal set of weights, they become more and more different. I think that's one sort of mental model people could have as to what's going on here. So I think you can, so in short, a lot of the training that happens during federated learning is still centralized learning. It's just happening at the client, many of those steps. And then the only times that information leaves those clients is simply to find this average point between the weights that the client thinks are ideal for its data and the weights a different client might think that's ideal for its own data. So but it's a natural question because it's definitely there's no point in a conventional machine learning course that talks about any of this kind of operation.
I think it's a great way in which you framed this, in the sense that a lot of the training that happens in federated learning is still centralized learning, because I think it's a good frame of mind to think about it like that. You have instead of just having one single centralized training, you have a number of centralized training, and then federated learning is sort of an orchestration layer above those centralized trainings. This is also from a framework perspective or programming perspective. This is a little bit how Flower looks at this, because it tries to make it very easy for you to take any kind of centralized project, any kind of regular, in quotes, machine learning project that you would find on GitHub or elsewhere. Our goal with Flower is to make it very easy to just take that project and then to plug whatever centralized pipeline is in that project, plug that into Flower as an orchestration layer to provide the federated layer above it.
Yeah, perfect. I saw two questions. One question that came in with respect to Flower datasets. And so the question is, does Flower dataset contain vertically partitioned data? If so, are there any examples that you can point me to? Javier, do you want to take this one? Or
yeah, so Flower datasets, just as a general definition, what it allows you to do is to make use of any of the datasets that are available currently in Hugging Face datasets. Is over 180,000, plus any dataset you might have locally that you want to make use with Flower datasets. And then you can partition this dataset making use of any of the features in such datasets. So for example, if you go to Hugging Face and you look for any dataset, let's say FedMist or Cypher 10, you will see that there are different features like class label or user ID or things like that. You can partition them along those columns using any of the partitioners available. For example, ID, Dixlet partitioner, shard partitioner. There are, I think, over 10 partitioners. And you can customize them to a very high degree. You can create your own partitioner as well. To the specific point of vertically partitioned data, I think you can partition them in a way that makes sense for vertical FL. I guess that's how you are. That's what you're thinking about when asking this question. Currently, we don't have an example for that, but there will be an example very soon.
yeah, so I guess that anyone could take Flower datasets and start to use them in a vertical way. There's something preventing you doing that, I think. Okay, and another question we have, it's quite a specific question, but perhaps it's been encountered by some of the people taking the course. Essentially, the course in course 2, because we use models that are much larger than the virtual machine instances that deep learning AI is used to provisioning, we had to use a third-party LLM provider, and so we used Fireworks, and they let us. We're using that service to run inference over the models that you can inspect and experiment with, and so forth. And if you look in the code, there is a variable Fireworks API key. The question that we got was, where can I get the Fireworks API key for part 2 of the course? And it says, looks like the centralized LLM fine-tuning notebook requires that. And so the answer to this is that if you're running the notebook inside the DeepLearning.AI environment, all of those commands will run. And this variable is populated, the key is populated by the Deep Learning AI proxy. They'll use a key that's coming from Flower to pay for the Fireworks inference. Now, if you run that within the Deep Learning AI sort of environment, those commands are going to run. And so you can run them as much as you want. You can try different sentences, different prompts out, and basically experiment with those models in the context of the course, fine. And what I think might have happened is if you take that code outside of that environment and you try to run it on your own machine, at that time, you'll need to provide your own Fireworks API key. And that's because we can't give our key out publicly, but we can allow these courses to be happening through the insertion of that key through the proxy. So that's what I believe is happening here. Okay, so that answers that question, quite specific to the course. Let me look around for other questions that we have. Oh, yes. Under federated learning, what happens if a client drops? Will it force us to restart the training from scratch? Is all hope lost if you have one of these clients that's participating, giving you information, doing part of the work, if one of them dies, stops responding, do you start from scratch, or what happens at that stage? Who would like to take this one?
I can take it. And maybe others want to add something to it, but I think the gist is all hope is not lost for sure. So federated learning is built with that in mind. Individual clients might drop out of a single training round, and that's oftentimes not a problem at all. And the way this works is that usually if you have a large number of clients, then you would select some of those clients. If we stick with the Google keyword example, where you have hundreds of millions of clients, then not all of those clients are online at the same time, but still a pretty substantial number of clients are online at the same time. You would not want to send a training task to all of those clients at the same time. So what you would do is you would sample a certain number of those clients, maybe a few hundreds or in the low thousands, and then let's say if you sample 1,000 clients, you would send the training task to all of those clients, and then chances are pretty high that some of those clients are dropping out. So instead of returning a result, you would just probably never hear from them again. And so what federated learning does in this case is it would set a certain threshold where you can say, okay, I'm selecting 1,000 clients and I expect to receive at least 500 results, let's say. So if that is the case, if you receive anywhere in between 500 and 1,000 results, then everything is fine. Those results will be used, they will be aggregated, and then the training will proceed as normal. And the ones that do not return a result, they're simply being ignored. Now, what happens if you receive less than those 500 results? In that case, the single training round and the example, the results you received from those clients, they would simply be discarded. So we would say up to this point, we had a certain number of federated learning training rounds, and those were successful. But then there's one round where we don't get a sufficient number of results back from those clients. We would simply say, okay, all of the results that we got, we'll simply ignore them, and we'll go back to, we'll simply restart the round. So out of the clients that are then available at the end of this discarded round, we would say, let's select another 1,000 and let's retry. And then let's see if this time we receive 500 or more results. And this is sort of the simplest way in which federated learning can handle this. It's like the most basic version of it. And there's many more sophisticated versions. There's also versions where this happens on a rolling basis, or more of a type of rolling basis, which is called asynchronous federated learning, async-FL for short, where even if we pass a certain threshold, we would aggregate on a continuous basis. And then if we receive results from a way earlier round, if we receive results very late, we would still factor them into the aggregation, but we would not weigh them as heavily as we would weigh new results. And there's many different variations, but this is sort of the most basic way in which federated learning can deal with clients that are dropping out of a single round.
I would like to
Great.
just add to that. That's what Daniel explained in a very good way, is that it's the cross-device setting in federated learning. We also have cross-silos setting, which usually you have a small number of clients, but with very good computation and good data sets. So in those settings, suppose you have like 3 hospitals and you want to do a federated learning on those data sets, and their data sets, if one hospital actually drops, then maybe you need to wait to have that client and that hospital back to continue the training, because that hospital is contributing a lot to the model with its data set. Just to add that we also have the cross-silo sitting in federated learning as well.
Yeah, it's important. It's good. In fact, I think it's a difficult area because under the same umbrella of federated learning, we try to attend to the needs of cross-device and the needs of cross-silo, and they really are just so different in some of their kind of characteristics and requirements. Cross-silo, for example, being just so much more stable and managed in some sense. Okay, let me just look for other questions here. Oh, the next question here is an interesting one. The question is, what was it like meeting Andrew? So, yeah, interesting. What would you say, Daniel?
I mean, for me personally, it was definitely great to meet Andrew, especially since I started out my journey in federated learning, and before that, just regular machine learning using his original course. So after having spent many hours on that course and then on some of the other courses he did with well, first it was just on Coursera, and then later courses about neural nets were provided by DeepLearning.AI. Before that, I think DeepLearning.AI didn't even exist. And so I spent a lot of time on those courses. So given that, it was a special experience to then stand in front of the camera with him for one of these courses, for sure.
Yeah, I'd like to say also add that it was fascinating to me to see how the machinery works, how these courses are made, how much thought that goes into how he and his staff think about the design of these courses and the other ones that they make. Yeah, it was really interesting to see how everything was put together. It was a really good experience. I think we learned, I think at Flower, we've learned a lot from, because it's so important to us as in terms of being able to help people and understand how to use federated learning and other related methods. It's really important to us to sort of maintain that outreach. And there's like so much we could learn from him and his team in doing this. So through these courses was really, I think, a valuable experience in that way too.
And I want to expand on one of the things you mentioned. One of the things that's maybe not so obvious when taking a course. When taking a course, there's one usually sees just an instructor that's standing there. But then behind all of these courses, there's actually a huge team of people who make that happen. And so at this point, I would like to say thank you to Andrew, but also to the entire team at DeepLearning.AI and the entire team at Flower Labs for supporting all of this and helping to make these courses happen. This was really a big team effort from both DeepLearning.AI team and Flower Labs team.
Absolutely. So a few more questions here. The question is, you discussed differential privacy in the course. The question is, are there other techniques available? I suppose in the course, or maybe within the context of Flower, or perhaps generally speaking, are there other techniques available? I think it'd be logical for Mohammed to take a crack at this question. So just again, question is, our courses have discussed differential privacy, and then are there other techniques available? What's the landscape like?
So I suppose the question is about techniques to provide privacy. And the answer is yes, there are techniques that goes under the category of secure aggregation, which basically they try to preserve the utility so they don't affect the utility that much, and they provide privacy for the clients. So in Flower framework, we currently support techniques like secure aggregation, or you can use libraries like you can use homomorphic encryption libraries in Flower basically to provide privacy for the clients. But those techniques, they usually have the disadvantage of being computationally expensive. And you need to consider that, especially if you increase the number of clients, those techniques become very heavy to run. Yeah.
Great. Yeah, because I just remember we've, for example, done examples using homomorphic encryption as well. And there's quite a like a spectrum of techniques, all with different trade-offs out there, all supported under Flower in different forms from different contributions from the community and so on. Another question here, it's quite a straightforward one. It says, will the courses be available till when? And I believe they'll be available for the foreseeable future. They're not going to go away, next week. It's not a limited availability. I'm not exactly sure. We were not told exactly how long they'll be available, but they should be available for the foreseeable future. It's the way to think about it, I believe. Let's see. Checking the different places where we get questions from. Okay, here's a question. Will this work if the links are slow? And there's a follow-up related question. And how much slower is the training compared to centralized? I think the first question is much easier to answer than the second one. But who wants to take a stab at this first question?
I can answer the first question.
Okay.
I'll give you the difficult one.
Okay.
So yeah, if the connection links between the clients are slow, well, this will, of course, slow down the training process. But there are many things that you can do to speed it up. For example, and one of the obvious ones is that in many circumstances, you probably don't need to train the whole model in Federation, maybe because you're starting from a pre-trained model. If that's the case, what you're doing effectively is federated fine-tuning, which allows you to only communicate the much smaller part of the model weights. This, for example, this is precisely what we do in course 2, where we only federate the fine-tuning of the LoRa adapters of the LLMs. And it means that instead of communicating 7 billion parameters, we communicate just a handful of megabytes. But there are other techniques, like if you really need to send an entire model, you can use techniques like quantization or any other type of compression mechanism, even those that are not exclusively designed for federated learning. Yeah.
So the other question is, so how much slower is this training compared to centralized? And it's quite a complex question. One way to think about this is it can be often much slower. So if I'm just thinking of examples that we see in the literature from organizations like Google and others who are building big federations. And they report often on the order of days to complete rounds. And the reasons for that is that they are building their federated models from the contributions of small devices. And then they and people who deploy those types of systems are often concerned about privacy to a very large extent. And so they want to make sure that there is a critical mass of devices available within each round. And then they don't have the ability, for example, to address individual clients to restart connections because they want to keep that connection or that possibility off the table, because that further reinforces things like security and privacy and all these things they really care about. And so for those reasons, rounds can take a long time because if a client is not available, then they have to find another set of clients to be able to complete that round. On the other hand, federated learning is a method by which you can combine different types of large servers together. And so those kind of more stable servers, they're not phones, but they might be GPUs run by hospitals, GPUs run by other organizations. They're far more stable. Those links are going to be far faster. And for that reason, depending on the nature of the federated training you're doing, they can be much, much faster than that type of timescale. And then the reason why it's a bit hard to say exactly how fast those rounds are going to be, and therefore how fast the whole training is going to be, is that it depends on a number of factors: how big the model is, how fast those links. Are you doing sort of federated learning with full participation, meaning all clients are part of each round, or partial participation? But there's no reason why you can't do federated training under those circumstances at the order of days to complete a whole training session, or even hours. For example, if you are fine-tuning an LLM potentially, where you have a small number of clients participating, those clients happen to be not in the same data center, but they happen to be spread. Well, if you're just doing a fine-tuning, as you saw in our class, the amount of data that needs to be exchanged, and therefore the speed by which you could do that fine-tuning, can be quite rapid. So it all depends on what you're trying to train. I think most importantly, where we see that federated learning as having a role, is that it enables types of training often that you just can't do with a centralized setup. And so in that context, sometimes it doesn't really matter what the comparison to a centralized would be, because that's more of a hypothetical situation that's best debated by academics. If you really want to train useful models, then federated learning shines under certain circumstances where centralized is not an option. And so the question is, can you train the model in an amount of time that is reasonable for the type of model you're trying to train? So on the order of hours to fine tune an LLM on private data, given there is no other option, is often fine. That's one way to think about it. But very, very natural question. Anyone else want to chip in here, or on a different angle? I'll just look for other questions in case. Let's take one more question. Yeah, and that question is a federated model always going to be worse than centralized? That's a viewpoint that sometimes comes up. And I mean, I think this is open for discussion. Again, it's similar to the speed issue. It's quite a complicated area. And so it seems good to end our AMA on this question. Does anyone want to take a crack, and we can just discuss this?
Yeah, I'm happy to make a quick comment about this. Very clear no. The whole point of federated learning is to train better models. And you would train better models because you can, by using federated learning, you can access data that you couldn't access before. So similar to the Google keyboard we discussed earlier, where there might be some pre-training on centralized, on public data, and then the training would be continued on new data that is on user devices. You could never train such a model in a purely centralized fashion, because the data you can access in a centralized fashion, data that's public or data that's possible to collect in a central place, is just more limited. And by going federated, you can access more data and you can train better models. That's the whole point of federated learning. It's a similar case in the cross-silo setting, where you have different organizations, for example, collaborating with each other, or sometimes also just a single organization that has distributed data internally. So that's, for example, something we hear out of financial services, where data sits in different regions and it cannot be combined in a single region. So even there, within a single organization that has all their systems in the cloud, data is in different regions, it cannot be centralized. And so one cannot train models on all the data if it's not if you're not using federated learning. The comparison, I think, that's sometimes being made, and that's just fundamentally pretty wrong from my perspective, is to take a public data set and then partition the public data set and then train one model on all the data in one data set, and then train a federated model on this partitioned data set. In this case, federated learning, depending on how you build up those partitions, federated learning can get extremely close to the centralized model. But if you build the partitions in a very adversarial way, then a performance of the federated model can be worse. But this comparison that you sometimes see in research papers is a pretty artificial and theoretical one. It's not really one that is actually reflecting any real world scenario. In the real world, the decision is not so much, do I have the data centrally, or do I partition my data? But the question is really, my data is partitioned anyways, and there's nothing I can do against these partitions. For example, in a healthcare setting, data is distributed across different hospitals, and there's just no way to put this data ever in a central bucket. So the question you're facing is a very different question. The question you're facing is, do I train a model on just a single one of these data partitions, on just the data that I have in this single hospital, for example? Or do I build a federated system that spans a number of hospitals, and do I incorporate their data into the training in a federated way as well? And so in that, if you think about it like that, then it becomes pretty obvious that the federated model has a much, much better chance at being a good model. And in many, many cases, actually, going federated is the only way to train a competitive, good, modern model architecture. Because modern model architectures, we all know this, they are very data hungry. If you think about any kind of meaningful, fully sized neural network, you need a lot of data to train these models. And then oftentimes you're often in the situation where just if you're a single hospital, you don't have enough data to train these model architectures. So the only way to actually train them is to go federated. And that's one of the big things we're trying to achieve with Flower. We're trying to democratize this way of training models, to bring those advances, to bring those new model architectures to industries or to sections, to task domains where previously it just wasn't possible to train these models.
I think you nailed it. That was a great answer. So perfect. Yeah, I completely agree. You only really want to use federated when you actually are going to be able to improve a situation. You wouldn't necessarily have the exact same identical situation, other than if you want to just query it for academic reasons. Okay, well, that brings us to all the time we have for this AMA. It's a bit of an experiment for us. First time for us to launch courses that are so publicly available. And so we thought it would be wise to start to run a few AMAs and to see what the students want, basically, what people out there want. We're happy to kind of align with the needs there. So we've tried to run this and answer some of the questions that have piled up over the last few days. I'm going to end by just showing you again, if I can find there we go. I'm going to end by just showing this. I seem to have picked the wrong thing. There we go. That's better. This is the slide here that explains the course. If you're interested in this course, feel free to follow this URL that you see there. you'll see two courses available from DeepLearning.AI on the on sort of the basics of federated learning. They're free. They're available right now. You get the slides plus some real hands-on code that lets you sort of start to do federated learning for yourself. We'll be delighted if you take these courses. And then if you want to follow up and ask following sort of questions, then we have a Slack channel dedicated on the Flower Slack to answering those questions. Yes, so we hope that you enjoy the courses, and thank you for joining us today. We hope that Federated Learning does everything you need. So with that, thank you all.
Thanks, everyone.
Thank you. Bye.
Thank you.
Bye.